Hello, this is Stylianos. I'm a physics teacher with ATS in Align, and in this video we'll try to solve the first question from the 2021 AP exam in electromagnetism. This is the exam paper, and let's scroll to question 1. Before that we see the basic constants and a list of rules that we will need. If necessary, we'll go back to see them if we forget something, and some tips for calculus and geometry. And here's our first question, where we see a system of a few resistors and a few capacitors, so a variation of an RC circuit. The capacitors will be charging or discharging. So quickly we see that we have an ideal battery, resistors and capacitors with given values. And the capacitors are initially uncharged. This is a little bit important. And the switch S is now closed. Okay, so when we close the switch, current will start flowing from the battery. It will reach the first junction, and since the capacitors are still on the process of charging, all the current will flow towards the capacitors, because when the capacitors are uncharged, they act like bare wires. So initially, at time is equal 0, there will be no current in resistor 2, and there will be no current in resistor 3. Current will flow from the battery to the first resistor, and it will be used in order to charge the capacitors. Later, when the capacitors are fully charged, they act like infinite resistors, so there will be no current used in order to charge them anymore, so all the current will flow through the resistors a long time later. So initially, the only thing that is happening is that current is flowing only through the resistor 1, so the R equivalent is equal to resistor 1 is equal to 100 ohms, and the current 1 is equal V. Actually, we cannot calculate directly the current 1, we'll calculate the total current, but we can say that the current 1 is equal to the total current because it is connected directly to the battery. So it will be V total over R equivalent, so it will be 10 over 100, it will become 0.1 ampere. And this is our final answer for part A. And we continue to part B, where it tells us that this switch has been closed for a long time, the capacitors are fully charged, the circuit has reached the steady state, and we need to find the potential difference across R1. Now, the current will not be the same, so I think that at least it will not be the same, so we need to find the new value of the current 1 in order to find the potential difference through R1. So, since the capacitors are fully charged, it means that there is no current through the capacitors, all the current flows through the resistors, but we need to find the total resistance, the equivalent resistance, starting with the two resistors that are in parallel. So, the R23 is equal to 1 over 30 plus 1 over 60 to the power of negative 1, because they are parallel. So 2 over 60 plus 1 over 60, 3 over 60, and if we flip it, the result is 20 ohms. And the total resistance, the R equivalent, is the R1 plus the combination of 2 and 3, so 120 ohms. So the total current, it will be V total over R total. So the V total is 10 divided by 120. This is 1 over 12 amperes. However, because the battery and the first resistor are directly connected, so this is actually the first current, the current through R1, so 1 over 12 ampere. And from this we can find the voltage 1. V1 is equal I1 times R1. This is 1 over 12 times 100. So 100 over 12, this will be around 8 this is 8.33. 8.33 volts, which is our last answer. Nothing difficult so far. And later we need to calculate the charge stored on capacitor C2. Now, there is no way we can find directly the charge stored on capacitor C2. Sooner or later we're going to use C2 is equal Q2 over V2, but somehow we need to find the voltage too. And this is a little bit difficult because the second capacitor belongs on a system of two capacitors that are connected in series. So we will say that since it is connected in series, since these two capacitors are connected in series, they will have the same charge, like the equivalent capacitor. So we can say that the that the Q2 is equal to the Q of the equivalent resistor, 1, 2. And this will be the capacitance of the equivalent capacitor, C12, times the total voltage for 1, 2. So we don't need to do that. Now, the capacitance 1, 2, it's not difficult to find. So we'll say they are in series. So 1 over 10 plus 1 over 15. We don't need to convert to with 10 to the power of negative 6. The result will be in microfarad. So 3 over 30 plus 2 over 30 is 5 over 30. And if we flip it, it will be 6 microfarad. And somehow we need to find the voltage, but we already know that the voltage for the first resistor, it is 8.33. So the remaining voltage for the other two resistors, it will be 10 minus 8.33, so it will be 1.66, 1.667 in reality. These resistors are in parallel with the capacitor 1, 2, so they will share the same voltage. So we can say that the voltage 1, 2 is 1.66 volts, or 1.667 volts. And now that we know this, it will be easy to find the Q2, which is 6 microfarad times 1.667. I believe that this will be 10. And because we're having microfarads, the result will be in microcoulomb, which is our final answer again. We proceed to part C2. The charge on the capacitor C3 is greater, less, or equal. Well, the capacitance 1, 2 was 6 microfarad. The capacitance 3 is 20 microfarad. So since they have the same voltage because they are in parallel, they are connected in parallel, so they have the same potential difference. This means that the capacitance 3 will be greater because the C is equal Q over V. Q over V, and the Q is proportional to the capacitance. So the charge stored on capacitor C3, yes, it will be greater than the charge on the capacitor C2 because the C is greater and the V is the same. And we continue to part D, where the switch S is opened. Okay, and we need to determine what will be the current in R1 and what will be the current in R2. Now let's first find the switch. So we had the steady state, so there was a value for the current. We open the switch and the battery does not provide current anymore. What provides current is the capacitors. The capacitors are discharging, so current will flow to R3, current will flow to R2, but it cannot flow to R1 because the switch is open. So for sure there will be no current in R1, so the current 1 will be 0. And we need to find the current 2. The current 2 will be V2 over R2. The V2 was the same voltage that we had before, like the initial voltage was 1.67 and the R2 is 30. So 1.67 divided by 20, I think, sorry, 30. And if we bring this into the calculator, the result is 0.056 ampere. Nice. And easy. So immediately after the switch, quite easy. Nothing really hard. And later we need to sketch a graph for the potential difference of the capacitor 2 after we open the switch. So the capacitor is discharging, so the potential difference will be decreasing. Less charge will lead to less voltage, so it will decrease exponentially. However, we need to label the maximum value. This might give us a little bit of trouble. We need to find what is the voltage of the capacitor at the start. Now, I guess that we'll use C2 is equal Q2 over V2. The C2, I believe it was given, 15 microfarad. The Q2 is, we had found it, 10 microcoulomb over V2. So the V2 is 10 microcoulomb divided by 15 microfarad. The micros are cancelling, so we can use these values. So the V2 is 0.67 volts. And because the capacitor is discharging, the potential difference will be decreasing exponentially with the trend to become 0 when it is fully discharged after some time. And the capacitor C3 is replaced by two capacitors, 10 microfarad, and eventually again when we close the switch, okay, the circuit will reach equilibrium. And then we open the switch again, so the capacitors will discharge, and for the time that it is greater than 0, would the sketch of the graph be above, below, or the same like the sketch of the graph. Basically, we need to see how the capacitor will be discharging, if it will be discharging more rapidly, less rapidly, or in the same way. Now, I believe that the voltage will be the same, the initial voltage. The initial voltage only depends on the battery and the resistors. However, instead of this capacitor, now we have two capacitors of 10 microfarad. I believe that this will change the time constant because, if I remember correctly, the Q as a function of time is equal the initial charge, this doesn't change, multiplied by e to the power of minus time over the arc C. So the C is the total C, the equivalent capacitance for this system of capacitors. And if we replace the C3 with two new capacitors, so 10 and 10, the equivalent capacitors for these two will be 1 over 10 plus 1 over 10 to the power of negative 1, so this will be 5 microfarad. And these two capacitors together, I believe we had found the capacitance to be 6 microfarad, and the system of the other two is in parallel, so 5 microfarad. Before the total capacitance was 26, now it becomes 11. So the RC gets a smaller value. This means that the capacitance will be, the time constant gets a smaller value, so it will take a little bit longer to discharge. Yeah, we can say that, let me just make sure that I didn't make any mistake in my calculations. The time, the C equivalent, the total capacitance before it was 6 plus 20, it was 26 microfarad, and it becomes 6 plus 5, it becomes 11 microfarad. So the capacitance decreases. The time constant is RC, so the time constant also decreases. And let me just copy and paste this because we will need it. So the time constant decreases, and this means that it will take less time in order to discharge. So since the time constant decreases, it will take less time in order to discharge. So the new diagram will discharge in less time. So the new line will be below. And we need to explain this with a few words. So it will take less time to discharge. So the graph will show a more rapid discharging, more rapid discharging, and the graph will be below. The new line will be below. I think this is the end of part 1. Yes, it took a little bit longer, especially the last part, I think. However, it was an interesting question, I believe. The first parts were on the easy side for the RC circuit. Simple, okay, the circuit looks complicated, but in reality it is on the simple side. Feel free to comment if you have any suggestions or any questions. Thank you for watching.